Hey there, welcome to 8-3. We are talking slope fields, and in this video, we're going to take our knowledge of differential equations and we're going to apply it graphically into one application, which is called slope fields, okay? So here we go. A slope field is a graphical representation of a set of slopes obtained from a differential equation. So remember that when we take a differential equation, that's a derivative, okay? And it can represent slopes of a function. Well, we know that there can be multiple slopes or just a particular slope for one certain type of function, depending upon kind of like, you know, the derivative that we take. So here it says even if you cannot separate variables and integrate, you can still use the differential equation to plot the slopes of a function. So here, example 1, it says find the slopes given by the differential equation dy dx, okay, so that's the slope, is equal to negative x comma y at the following points. Well, they give us points, and these points represent an x and a y. So if the slope dy dx is negative x over y, then here my slope would be negative 3 over 2, right? Very, very simple. Okay, for b, it's going to be negative 1 over 3, which happens to be 1/3. Simple enough. All I'm doing is plugging in x and y. For c, I have negative 2 over negative 1, so that's 2 over negative 1, which is negative 2. And for d, using the same idea, we have negative 2 over negative 2, which is 1. So this represents the slope, right? This is the slope for a function, okay, at different points. So depending upon the point, the slope could be different. So here it says, well, why can't we find the slope when y is equal to 0? Well, for this particular equation, right, we have a denominator of 0, and we cannot divide by 0, right? Cannot divide by 0. So what happens, right, is that at 0, it's non-differentiable, right? So dy dx is non-differentiable at 0. At x equals 0, y equals 0, Schwarberg, okay, at y equals 0. All right. So here is a visual example of a slope field, and it looks kind of trippy. But what you should be able to see if you kind of look at them once we have our actual slopes is kind of the image of a function embedded within that. So here, this example says, find and plot the slopes given by our differential dy dx is equal to negative x over y for each remaining marked point on the coordinate plane at the right. So what I'm going to do, I'm going to go ahead and complete this slope field. They've done some of them for us, but I'll go here, right, to point A. So 3, 2. I know the slope is negative 3/2. So 3, 2, right? And here's that slope, 3/2. Okay, at negative 1, 3, the slope is positive 1/3. Okay, here at number part C, negative 2, negative 1, the slope is approximately negative 2. Okay, so they have all of these slopes for all of these values, and what we can do is complete it by going to the points. So what about what about point 0, 1? So here, well, again, my function is negative x over. Siri's talking to me. Is negative x over y. So at 0, 1, again, my x value is 0, so I'm going to have a flat slope like this, okay? And that would just be for any x value, right? Because all my x values are 0. So here's my just a little line of kind of what the slope would be for this differential. Now I can go ahead and I can choose like another point. So let's just inspect another point. Let's say 2, negative 1. So at 2, negative 1, right? The slope is going to be, I'll just say y prime will be negative x, so negative 2 over negative 1, which would be 2. Okay, so from here, you can imagine going up 2 over 1, right? And just kind of connecting a line. So it's a steep line like that, right? Okay, so I mean, that's what it is. So, and then I'll go ahead, I'll do another one. So what about -2, +1? So -2, comma, +1. Well, y prime would be, so -2, so it would be +2 divided by 1, again, would be 2, right? So something like this, right? Up 2 over 1. Okay, and you can kind of imagine extending a line. Okay, so that is what a slope field is all we're doing is just drawing the slope for our differential at these points. Okay, and so I'm going to go ahead, we're going to complete this for all of these, and we can go ahead, and I hope what you can see is kind of the general shape of a function. Okay, right. Okay, so all I'm doing is just this whole process over and over again. Okay, and I think I have them all. Okay, so that is a slope field. That's how you generate your slope fields, by plugging in the points into the differential. So what do we do with slope fields? Well, here we're going to go ahead and see in example 3 what they kind of want us to do. So it says in example 2, you made what is known as a slope field. Starting at the point 0, -3, follow the flow of the slopes to sketch the solution curve containing 0, -3. Your graph should be parallel to the slope lines and be like an average slopes whenever it goes between lines. Your solution curve must represent a function whose domain is the largest possible open interval containing the given point. Okay, so again, I'm going to go ahead and I'm going to sketch a solution curve, so one particular curve containing this point 0, -3. And then they say the graph should be parallel to the slope line. So we're going to kind of like pass through the lines, and if we go in between, it will be like an average of the slopes. And it must represent a function. Okay, and they say down here, note, the most common student error in sketching a particular solution to differential equation is to extend the sketch too far and create a graph which is not a function. How do I know if something's a function? Well, your vertical line test. Remember that it cannot pass through a vertical line more than once. It is important to set boundaries for your sketch. So, like, why would the x-axis in this case be an appropriate boundary line? Well, I don't have any differentiability here, right? So, and if you kind of look at this, you can kind of generally see it looks almost like a circle, right? So, but a circle is not a function. So let's go ahead and we'll look at this kind of example here at 0, -3. Okay, 0, -3. So that is down here, 0, -3. Okay, so at this point. So I want to go ahead and I just want to draw curve. I kind of want to go with the flow. Go in with the flow. So notice my slope looks like this. Okay, I'm about here, kind of getting steeper, and then I get to here. Well, at my x-axis, right, non-differential, so I have open circles. Okay, and that is slope fields. That's it. Actually, this side should be more. About there. Okay, all right, so that is a slope field, and then they want us to go ahead and then do it again for the point -1, 1. So -1 up 1, so that's this point here. So I can go ahead, sketch a curve that would look something like this, and then one more 0, 1. Okay, 0, 1, that's right here. So that would look something like this. Okay, and that is a slope field. All right, pretty simple, right? Okay. Okay, so we're going to go ahead and do example 4. It says solve the differential dy over dx is equal to negative x over y. So we'll go ahead, we'll multiply both sides by y, so we get y dy, and we'll multiply both sides by dx, so we have negative x dx, and then we're going to go ahead and integrate each side. So we now have y squared over 2 is equal to negative x squared over 2 plus c. And what we're going to go ahead and do, we'll multiply both sides by 2. So we get y squared is equal to x squared plus c. And now what we need to go ahead and do is take the square root of both sides. So on this side, I have a positive, and there's a negative there. So negative x squared plus c, or it could be negative, right? Plus or minus. That's kind of the moral of the story that we're trying to get at. So negative x squared plus c. So I have two different solutions, right? So do the possible solutions verify your results from example 3? So if we go back and we look at this, right? Look at these different curves. Does that kind of look like those functions? And the answer is yes. So here it says, remember that the solution to a differential equation is a function, and the particular solution will pass through a certain point. So I want to go ahead and I want to solve. What about through the point 0, 1? Okay, so notice that this point, right, has the y value that's positive. So I'm going to use my first equation. I'll take this and I'll plug it into here. So 1 is equal to the square root of, if I plug in 0 for x, it becomes 0, and I get c2. If I square both sides, we get c is equal to 1. So thus, our particular solution is the square root of negative x squared plus 1. Okay? Now we're going to go ahead and do the same thing for the point 0, negative 3, and I'll plug that into this equation. Okay, so we get negative 3 is equal to negative square root of negative x squared, which again is 0, so nothing happens there. And we get this, okay? So after we square both sides, we get c is equal to 9. Okay, so here is our particular solution. Negative square root of negative x squared plus 9. And there you have it. All right, that is it for this video. I'm going to go ahead, I'm going to stop it, and I'll make a second video for the last part of examples, okay? Catch you next time. Peace.